Now that we've discussed what a limit is, let's formally define it. So the definition of a limit is that if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L. So let's break that down. If f of x becomes arbitrarily close to a unique number L, and that word arbitrarily close just simply means that it's not specified what value we need to approach or hit. It's arbitrary. We're just saying as we get closer to some unique number L, some value, as x approaches c from either side, the limit of f of x as x approaches c is that number L. That's what we're saying. So it's essentially just summarizing what we talked about in the previous video. So what I want to do is take a look at a couple of problems and practice finding the limit both numerically and graphically. So let's take a look at this first example. I said the first example, not that one. All right, so let's take a look at this first example. So we've got another rational function here, and we're looking at what the limit of this function is as x approaches 0. So if we know we want to find a limit as x approaches 0, let's find some values to the left and to the right of it. And let's not go too crazy here. Let's just choose some integer values on either side. And just take your calculator right now, and you can either just put in this function and then just look at the table, or you can put it in Desmos, whatever works for you. And you should get the following values. Okay, and again, you can just use your calculator just to evaluate. So numerically, we're looking at what's happening to this function as x approaches 0. So as we approach 0 from the left side, we see a value we think it's getting closer and closer to. And then as we approach 0 from the right side as well, it also looks like we're getting closer and closer to value. Can you figure it out? Yeah, it would be 6, right? And we would say just be careful with our limit verbiage here. We would say as x approaches 0, the limit is 6. And again, in this example here, we are not saying that f of 0 is 6. In fact, it's not. F of 0 is undefined. So how can we confirm this in our graph here? Well, just kind of looking at a couple of the values here, and some of this you can kind of just do analytically. For example, if we plug in -9, we should get -3 in the denominator, which would give us -9, +3 up top. Okay. And then at 0, we already figured that out. That's going to give us an undefined value. But we see that it's getting closer and closer to that 6. So our graph should actually look like this, where we would have a hole up here. So our graph looks like that. It's undefined at 0, but clearly we can see that in our graph, as x gets closer and closer to 0, our function gets closer and closer to the value of 6. So our limit is 6. Okay? All right, let's try another example. This time, we have a piecewise function, which is essentially just saying we've got two different pieces here. Depending where our domain is, our function is going to go and do different things. As long as our x value is not equal to 5, then our function is equal to 1. When our x value is equal to 5, then our function is going to give us an output of -2. All that means is at the value 5, we have an output of -2. Okay? So when x is equal to 5, f of 5 is equal to -2. Our output is -2. Everywhere else, our output is 1. So what would this graph look like? We're saying that for all other x values, our output is going to be 1. And that doesn't look very good. I'm going to try that again. Do this on the iPad. All All right, well, that isn't great, but hopefully I can move this up. Nope, can't do it. So I'm going to have no choice but to try this one last time. And I'll take whatever I get. Boom, I'll take it. Now, when our x is equal to 5, is our output 1? No, it's -2. So this piecewise has a hole up here, and it's going to continue being 1 everywhere else. Okay, so that's what our piecewise function looks like. So let's look at this graph and try to determine the limit. The limit of this function as x approaches 5 is what? And if you said 1, you're absolutely correct. It is 1. The limit of this function as x approaches 5 is 1. Is f of 5 equal to 1? No. F of 5, we're told, based on what we're given, is -2. So we'd say, as x approaches 5, the limit is 1. Remember, the limit is about what the function is approaching or how it's behaving, not what's actually defined at that point. We're saying that as we get closer and closer to 5 from both sides, our function looks like it's getting closer and closer to 1 pretty much everywhere else. Okay? All right. With that being said, let's really reinforce that idea. The existence or non-existence of a function at x is equal to c has no bearing on the existence of the limit of that function. And that's something that's kind of tough for some students to wrap their minds around, but it's really just reinforcing what a limit is. It's not about the defined part of the function. It's about how it's behaving as we approach a specific c value. So, one thing we haven't talked about yet are limits that don't exist. And there are 3 types of limits that don't exist. And quite honestly, some of them you won't really see very often at all in your calculus studies at the high school level, but it's important for you to know the 3 different cases. So the first one is a function that approaches a different number from the right side of c than it does from the left side of c. So let's take a look at an example of something like this. We're given another piecewise function. This time it's saying when x is less than 0, our function is going to look like 1. In other words, our output is 1. Well, that's pretty easy to graph. So for every x value that's less than 0, I'm just simply going to draw something like a 1. Oh, that's so much better than what I had before. Okay. However, when x is greater than or equal to 0, then we have the function x plus 2, which just means I have a y-intercept of 2, slope of 1, so our graph is going to look something like this. Okay? And again, just to revisit how to graph piecewise functions, they both can't be defined at different points for x is equal to 0. We know it's undefined for this piece, so I'm going to draw a hole there. Okay? So here's our piecewise function. Now let's look at what we call one-sided limits. So pay attention to this notation down here. We're saying as x approaches 0 from the positive, that's how we read that, as x approaches 0 from the positive. In other words, as we approach 0 from this direction, what does it look like our function is getting closer to? Well, it looks like our function is getting closer and closer to the value of 2, the output of 2. So our limit is 2. Now let's look at what our function is doing as x approaches 0 from the negative. This one right here, as x approaches 0 from the negative. As x approaches 0 from the negative, it looks like our function is getting closer and closer to 1. So what we're seeing here is that our one-sided limits are different. They're not equal to each other. There's a disagreement, if you will. As we approach 0 from the negative, the function is approaching 1. As we approach 2 from the positive, 0 from the positive, our function is getting closer and closer to the output of 2. So what we would say is the following. We would say that the limit as x approaches 0 from the positive is not equal to the limit of this function as x approaches 0 from the negative. They're not the same. Therefore, the limit of this function does not exist. Because our one-sided limits are not equal to one another, the limit of this function does not exist. Okay, so this is the first case of a limit that doesn't exist. Well, what are the other ones? So the second case is the function that increases or decreases without bound. In other words, the function is getting closer and closer to infinity as x approaches some value c. So let's go with an easy example for this. So look at the limit of the function 1 over x. Well, let's take a quick look at what this graph looks like. When x is equal to 1, my output is 1. When x is equal to 3, my output is 1/3. Well, what about when x is a fractional value between 0 and 1? For example, if x were equal to 1/2, then this would be equal to 2. If x were equal to 1/10, then my output would be 10. So this graph is going to look something like this on this side. And for negative values, it's really just going to be symmetric with respect to the origin. So you're going to get something that looks like this. So that graph is going to just look something like that. Pardon the sloppy graph. I'm trying to do my best. All right. So take a look at this function here. This is f of x. As x approaches 0 from either side, let's just look at it from either side. As x approaches 0 from the negative, as we get closer and closer to 0, what is f of x doing? Well, it looks like f of x is getting closer and closer to negative infinity. Well, what about as x approaches 0 from the positive? So use a highlighter there. As x approaches 0 from the positive, well, it looks like our function is approaching positive infinity. Okay? So there's actually two reasons here why this particular limit does not exist. There's two reasons here. The first is you can say from our previous example that the limit as x approaches 0 from the negative is not equal to the limit as x approaches 0 from the positive. I mean, we just established that from the previous ones. Both the one-sided limits have to be equal to each other, right? But in general, infinity cannot be a limit, right? It's not a specific value that you ever arrive upon. You never get to infinity and say, oh, I finally made it. I'm here, right? It's more of a concept than it is a quantitative value, right? So if we see that our limit as our function approaches positive or negative infinity, we can say that our limit does not exist, okay? Infinity cannot be the limit of a function. It can be used to describe one-sided limits, as we've seen in this example here, but it cannot be the limit of our function. And now our final case is probably the one that's the most unique and least seen in our calculus studies, but it's still the third case nonetheless. Any function that oscillates between two fixed values as x approaches c. So in this case, the limit of this function, cosine of 1 over x, as x approaches 0, and try putting this into Desmos right now, or put this into your graphing calculator and see what you get. What you're going to see is as x approaches 0, the closer it gets to 0, it's going to start oscillating between two values. And think about why this is the case. Think about why it would start oscillating between that. And the clues really being to do with the fact that cosine, in this particular case, remember, is a cyclical function. As x gets closer and closer to some value 0, to a value of 0, think about what that does for our argument. Ask yourself, what happens to those values? They are going to give us values that cause cosine to oscillate and flip back and forth between positive and negative values. And try entering in small values for x numerically if you're still having a hard time grasping this. Okay? So again, don't stress out too much about that last one. You don't see it too often. But what we're really seeing here is as x gets closer and closer to 0, our function cannot ever agree upon any one value. It's going to keep flipping back and forth between positive and negative ones. Therefore, the limit in this case does not exist. So there you have it. Those are 3 different cases in which limits don't exist. And of course, we will study this far more as we continue in our calculus studies.